Hello, good morning everybody. Today I'm going to teach you all Gauss's theorem. Okay, so before learning Gauss's theorem, we must know few terms such as what do you mean by electric field, which I have done already in the class, and after that we must know what do we mean by electric flux. This is very important, okay, because Gauss's theorem is related to electric flux. Okay, so what do you mean by electric flux? What is electric flux? Okay, so let's start the class with electric flux. Okay, just remember we are going to do Gauss's law or Gauss's theorem. Okay, Gauss's theorem. So in Gauss's theorem we are going to do, there is a term called electric flux. What is this electric flux? So we denote electric flux with the Greek letter phi, and this is phi, and at the surface we write E. So this means electric flux. Okay, so what is electric flux? So just remember, we all know that there is an electric field, that is, we denote electric field by the arrow sign. Okay, so this is a uniform electric field. Just remember, whenever we write electric field, it is always uniform electric field. Uniform electric field. Now, how can we produce this electric field? So we have already learned in the previous class that to produce electric field which is parallel to each other, means uniform electric field, there must be a plane charge, because we know when we keep a plane charge, the electric field which emanates from here is always parallel to each other. And we also know that the last, it moves like this, because transversely electric field repel each other. Okay, so but we are not concerned with the last one. We know that to produce a uniform electric field, we must have a plane charge, which is assumed, okay, that there must be plane charge. That's then only electric field was parallel. So whenever I draw electric field parallel to each other in this way, it means there is a plane charge. Okay, now when if we keep a plane surface inside the electric field, okay, what we are going to do, we are placing a plane surface in the electric field. So what happens? So we say the electric field which are linked to this surface is known as electric flux. Electric flux is always related to the surface area. Whenever we keep a surface in an uniform electric field, for example, suppose these are electric field, okay, the electric fields are parallel to each other. Now to calculate electric flux, we must always have a plane surface. Okay, so plane surface, for example, for instance, suppose this is an electric field, the electric field, okay, and here I have kept a surface, plane surface. Now we can place the surface like this, or along with the electric field, perpendicular to electric field, or in any angle. Okay, so here we have got electric field. Now whenever I talk about electric flux, there must be a plane surface. When there is a plane surface, I'll say okay. When there is a surface, I'll say okay. Now the electric flux linked with this surface is how much? Okay, now, so always remember the electric flux is always this electric field is always linked to surface area. Whenever we place a surface inside or within an electric field, then we say that how much, then the concept of electric flux evolved from there. Okay, now suppose so we write electric flux as phi E is equal to, there must be an electric field and there must be an area, because there must be a surface area. Now we call this A as area vector. We call this area vector. Now what is an area vector? Okay, now since area we know, suppose this is the surface, so this is the area. So how much will be the area? So this is length and this is breadth. So length into breadth, that is the area, length into breadth. Okay, now when we talk about vector, area vector, so what is area vector? So vector means it must have what? It must have a direction. It must have a direction. So this is the surface. Where is its area vector? So always remember that area vector is always perpendicular to the surface. If the surface is kept like this, the area vector will be this. Okay, now if the surface is like this, area vector will be like this. Means this area vector and this surface will always be perpendicular to each other. Okay, so we say area vector is always perpendicular to the surface. Area vector is always perpendicular to the surface. Okay, now so we have a formula for area vector is E dot A. Now E dot A, in class 11 we have studied about the dot product, or we call it as a scalar product and cross product. Okay, so we all know that dot product, suppose there are two vectors A, there is a dot product, so the magnitude of this will be AB cos theta. And if it is a vector product or cross product, then we write magnitude as AB sin theta, and there will be an unit vector, because A cross B is a vector quantity, the resultant will be a vector quantity, so it has got a direction. But A dot B is what? Scalar product, and we all know that scalar product don't have any direction, so AB cos theta, and there will be no direction, so AB cos theta. So from here we can say that this electric flux is a scalar quantity. So electric flux is a scalar quantity. So electric flux is what? E dot A, and if I write this as this will be EA cos theta, where E is the uniform electric field, A is the surface area, and cos theta. Now here the question arises, what is theta? Okay, so theta is the angle, it is the angle between electric field and area vector, that is A. Okay, so theta is the angle between electric field and area vector. Okay, see, I have drawn here the direction of electric field is here. Now what will be the area? See, this is the surface, and for talking about electric flux we must have a surface area. So we have a surface area, we have electric field, so we can talk about electric flux. Okay, now here is the surface area. Now where will be the what will be the electric flux? But before calculating electric flux we must know this area vector. So we have already learned that area vector is always perpendicular to the surface. So what will be the direction of area vector of this surface? So since the surface is like this, so area vector will be perpendicular to it. So we can say that area vector is in this direction. This is the direction of area vector. And what is the direction of electric field? Electric field is also in the same direction. So in this case we can say that theta will be 0 degree, because area vector and electric field both are in the same direction. Okay, now so in this case the electric flux will be EA cos theta, where theta is 0 degree, the EA cos 0 degree, and we know that cos 0 degree is 1. So electric flux will be E into A. This is the electric flux. Okay, suppose let's take a different case. This is the electric field, this is the electric field. Okay, Now if I keep the surface along the direction of electric field, always remember here the electric flux was, we call this electric flux as maximum. Why? Because we know that cos 0 degree is 1 and this is the maximum value of cos theta. So this is the maximum value of cos theta, so we call it EA is maximum. So for getting maximum electric flux, the area vector and electric field should be along the same direction. Okay, so area vector and electric field is along the same direction, then only we can say that the electric flux is maximum. Okay, now what we are going to do is, suppose if I keep the surface along the direction of electric field, what we have done, we have kept the surface along the direction of electric field. So what will be the electric flux linked with this surface? Okay, with this surface, what will the electric flux linked with this surface? So see, we know that phi E is equal to EA cos theta. Suppose the area we are taking as A, area is A. Okay, now next we are concerned with theta. So what is theta? So theta is the direction between electric field and area vector, not the surface, area vector. So this is the surface, so first we are going to draw the area vector. So area vector will be perpendicular to the surface. This is the direction of area vector. Okay, now this is area vector. Now electric field is in this direction. Okay, so electric field is in this direction, area vector is over here, so the angle is 90 degree. So we will say that EA theta is how much? 90 degree, because theta here is 90 degree, because theta is the direction between electric field and area vector, and we know that cos 90 is how much? 0. So electric flux will be 0. Okay, so always remember, whenever we are going to calculate electric flux, we must have electric field and we must have a surface area. Okay, and the theta is the angle between electric field and area vector, not the surface. Okay, now suppose if I say what will be the electric flux. Okay, what will be the electric flux? We have to calculate electric flux when electric field and surface is perpendicular to each other. Okay, it's perpendicular to each other. So electric field and surface is perpendicular to each other. So what happens here, the common mistake which students make. Okay, so what mistake they make? Whenever they see, okay, perpendicular, whenever they see perpendicular, they think that it is 90 degree. So cos 90 degree is 0, electric flux will be 0. Here they make lots of mistake, because here we have said electric field and surface is perpendicular to each other. I haven't talked about area vector, surface area vector. I haven't talked about. Here we have talked about surface area is perpendicular. Okay, so when surface area is perpendicular means this is the electric field. Okay, this is the electric field. Okay, now here the surface is perpendicular, surface is in this direction, surface like this. Okay, the same way, this is the direction of electric field and surface is perpendicular to each other. Surface is perpendicular to the electric field. Okay, now when surface is perpendicular to the electric field, it means to calculate electric flux, we must have EA cos theta. So electric field is E, and suppose the area is A. Okay, if this is a rectangular surface, the area will be length into breadth. If it is a cylindrical surface, the area will be the total surface area, that is 2 pi r to r plus is the top surface, the area of bottom surface, and the area of the curved surface. Okay, so here electric flux is EA cos theta. Now, so here theta, so surface perpendicular, so what will be the area vector? So area vector is perpendicular to surface area, which is actually along the direction of electric field. So here it will be EA cos 0 degree. Okay, so don't carry it away by just looking at the perpendicular. term perpendicular. Don't get just carried away. Why? Because who is perpendicular? The surface area is perpendicular, not the area vector. When area vector will be perpendicular, then the electric flux will be 0. But when surface is perpendicular, so first we'll get the area vector. So area vector is perpendicular to the surface. Now this area vector is perpendicular to the electric field or along the direction of electric field. Okay, so we'll think, so we have to take always the area vector. Okay, next. So we got the formula for electric flux. Electric flux is E dot A, or we can write this as E A cos theta. So we have studied about electric flux. Okay, just a minute. Okay, so we have talked about electric flux, that is E A cos theta. Electric flux is a scalar quantity, and electric flux is always linked with a surface, and this theta is angle between the area vector and electric field. Keep these things very clear. Okay, so one more thing, when area vector, and so to get maximum electric flux, to get maximum electric flux, always remember area vector and electric field should be along the same direction. Okay, suppose if I give you a question, suppose a surface, okay, is kept along, a surface is kept along, okay, along the direction of, is kept along okay. So the question is, a surface of area A is kept along the direction of electric field, then electric flux linked with that surface is, okay. So what they are saying, surface area is kept along the direction of electric field, means this is the electric field. Okay, so this is the electric field, and the surface is kept along the direction of electric field. Surface is kept like this, means electric field are in this direction, okay, are parallel to each other, and this surface is kept along the direction of electric field. Surface also kept along the direction of electric field. So the first thing which we have to make out is the area vector. So area vector is what? Perpendicular to the surface. It means it is perpendicular to the electric field. Electric field was in this direction and the surface is along, so the area vector is this. So electric field and area vector is perpendicular to each other. So we say that theta is equal to 90 degree, so phi E will be EA cos 90 degree. Okay, so cos 90 degree is 0, so electric flux is 0. So option B is correct. Okay, so I hope it is clear. Now here there was a surface, but suppose if there is a closed surface, for instance, suppose there is a cube. Okay, suppose there is a cube. This is a cube. Okay, now this cube is kept in a uniform electric field. Uniform electric field E. So how much is the electric flux linked with this cube? Is that clear? So till now we have studied that electric flux is linked with the surface. Now here I have asked you all to find electric flux linked with this cube. So the electric flux linked with this cube. So we all know that a cube has got 6 surfaces. So we'll calculate electric flux linked with each surfaces. Okay, very simple. So see, the direction of electric field is constant. Cube is kept within an electric field. Okay, so the plane charge is somewhere outside. Okay, now if suppose if I name the surfaces, okay, number the surfaces. This is surface number 1, this is surface 2, 3, 4, the front one is 5, and at the back it is 6. Okay, so let's talk about first surface. So the first surface is kept like this. Okay, so this is the surface, and here it is, electric field is here. So first we'll get what? The area vector. So area vector is perpendicular. It means what? Area vector is in this direction and electric field also in this direction. So electric field, the blue pen, and the that area vector, that is my red pen. Okay, both are along the same direction, both are moving in the same direction. So the angle between them is 0 degree. So what will be the electric flux? So electric flux will be EA cos 0 degree, and here we are talking about the first surface. So EA cos 0, so it will be EA cos 0 degree is 1. Next come to the second surface, this one. So here the area vector, so the surface, this is the surface, so area vector is always perpendicular. Okay, so now here this is the surface, area vector is this one, perpendicular to surface, and electric field, where is the electric field? So electric field is moving into the plane. Here the electric field is going in this direction. See, electric field is going in this direction, and area vector is over here. So we can say that area vector and electric field are opposite to each other, are in opposite direction. Means we can say the theta will be 180 degree. Why? Because see, electric field is in this direction and area vector is in this direction. So electric field is moving in this direction, area vector is here. So the angle is how much? 180 degree. So if I talk about, so the electric flux linked with the second surface is how much? So electric flux linked with the second surface, it will be EA cos 180 degree, and cos 180 degree is how much? Cos 180 degree is equal to -1. So this will be minus EA. Okay, next with the third surface, this surface, so this surface is like this. Okay, and electric field is in this direction and area vector is here. So area vector and electric field are perpendicular to each other, so it's very simple. So electric flux linked with the third surface will be 0. Similarly with the fourth surface will be 0. Okay, so fifth one here, so this surface, so see, if this is the surface, here the surface is facing this side, so the area vector will be in this direction. Okay, coming out in this direction, perpendicular to the surface. Okay, so this is the direction of electric area vector, and electric field is moving this direction. So this is the direction of area vector, and this, so this is again what? 90 degree. So for this fifth surface, again it is 90 degree, theta is 90, so again electric flux will be 0. And for the sixth surface, again here area vector is perpendicular to the electric field again, so again for the sixth surface it is also 0. So total electric flux will be how much? So for the first surface it is EA, for the second surface it is minus EA because it was 180 degree, third, fourth, fifth, sixth. For the other surfaces the area vector was perpendicular to the electric field, so all are 0. Now EA minus EA, So we will simply add y because electric flux is a scalar quantity. So for adding scalar quantity, we don't require direction. So plus EA minus EA 0, and so net electric flux linked with this cube when electric field when this cube is kept within the electric field, means the charge is kept outside the electric field, then the total electric flux linked with this cube is 0. Okay. Next, if suppose now suppose if there is a cube. Okay, this is a cube. Assume it to be a cube. Okay, it seems to be cuboid, right? Suppose it is a cube. Now if I place a charge q inside the cube, then what will be the electric flux linked with this cube? Okay, so what see, now we all know that if I keep a charge q, the electric lines of force come out from positive charge q. Okay, so this electric field will come out in all the direction from here. It will come from here also, it will move back also. Okay, so it will come out also and it will move back also. So here if we see this is the surface, and the electric field and the area vector will be also be in this direction. So with this surface, if I talk about the electric flux will be E into A. So electric flux linked with this first surface is E into A. Okay, now here the electric field is moving in this direction, because from this charge q, electric field will move out in all the direction. Okay, so in this case the electric field is moving here, and area vector is also in this direction. So again cos 0 degree is 1, so again plus EA. For the third surface, suppose this is the third surface, this one, this is the third surface. So electric field is moving in this direction, as well as area vector is in this direction. So if we see that, then electric flux linked with all the surfaces, all the 6 surfaces will be E into A. So it will be 6 E into A. So this happens when the charge is kept within the cube. It is very important. Okay, when the charge is kept within the cube, then net electric flux came out to be 6 EA, and when the charge was outside the cube, then the net electric flux was 0. Okay. So till now we have studied about electric flux, that how much is the electric flux linked with the surface, whether electric flux is a scalar quantity or vector quantity. So we have studied that it is a scalar quantity. Okay, next we have studied that electric flux is E dot A, and we call that EA cos theta, and theta is what? Angle between electric field and area vector, and area vector is always perpendicular to the surface. Okay, always perpendicular to the surface. Now, and then we have seen that how much electric flux is linked with the cube. But cube is what? Cube is a we can say a even surface, regular surface, where all the faces are equal. But if the surface is irregular or uneven, then how we will calculate the electric flux? Okay, so the second next part is electric flux linked with irregular surface. Okay, irregular surface. Okay, now suppose the surface is somewhat of this shape. Okay, now this is the electric field E. So alright, so this is the electric field. Now if we see, we can't, there are lots of surfaces. Okay, here this surface is in this direction, again here there is a curve, again there is different surface, again here the surface is different. Okay, so we have got a lots of surfaces. As previously I have said that in a cube there are 6 regular surfaces. All the 6 surfaces were regular, but here there are lots of surfaces. Okay, Acha, how can I say that there are 6 surfaces? How I have distinguished the surfaces? So always remember, while distinguishing the surfaces, what we do, we see that for this surface, the theta is common for all the electric field throughout the surface. Here in this surface, the electric field is acting in this direction, and area vector is also in this direction, so the theta is common. Theta is same for all electric field. But if I move on to this surface, here theta changes. So as theta changes, we say that surface has been changed. Okay, so if I see over here, this is the electric field. Where will be the area vector? So area vector will be perpendicular to the surface. So if I make area vector here, it will be somewhat like this. Okay, now the same, if I make area vector over here, this will be somewhat like this, 90 degree. So see, here the theta is different and here the theta is different. So here we can't make out, we'll say that this is a different surface, this is also a different surface. Okay, now how do we find electric flux linked with this? How do we find electric flux linked with this surface? Okay, now to find the electric flux linked with the surface, what we do, we take a very small surface and we call this surface as ds, because for this very small surface this theta will be constant. Again, if we take a very small surface over here, this theta will be constant for this surface. So what we do, we take a very small surface and we call that surface as ds. Ds means very small surface area, and electric field is E, and ds is where acting here, and area vector is, this is the area vector. Suppose area vector ds. Okay, so area vector ds is what is acting in this direction. We know that electric flux is, we have the formula of electric flux as E dot A. Okay, E dot A. Here we are taking very small surface area, so the electric flux will be very small, that is d phi E is equal to electric field is E dot very small area, that is ds. Okay, now to calculate the electric flux linked with this whole surface, then what we have to do, we have to integrate it. We use calculus here. Okay, so if we integrate this d phi E, here it will be de ds, we can write ds cos theta. Now if we integrate this, so this d phi E, this d phi E will become total. This was small electric flux. If I add all the electric flux with all the small surface, related with all the small surface, will get total electric flux. If we integrate d phi E, will get phi, that is total electric flux. Yet E is constant, and next theta will also be constant. Why? Because I have taken this small ds, and for this small ds this theta is constant, so we take out this theta too. So E cos theta. Next ds. So ds will integrate this small surface area. So this will be the total electric flux linked with this surface. Okay, now if this surface, suppose if this surface is a cube, is a cylinder, so we know the total surface area is how much? 2 pi r into r plus h. This is the total surface area of cylinder. So here in place of ds we will write 2 pi r into r plus h. Okay, now suppose it is a cube, so we will write 6, the area, total surface area, that is 6a square, where a is the side of the cube. Okay, so here we will integrate only ds, where E will be constant, it is uniform, and theta is also constant because we have taken theta constant for a very small surface area. Okay, now what so here we got a formula .ds. Okay, next electric flux linked with the closed surface. Electric flux linked with the closed surface. Suppose there is a cylinder. This is a cylinder of radius r, okay, and height h, and here it is electric field. Now I have to find electric flux linked with the surface. So it is very simple. We have studied electric flux linked with the surface will be E dot ds, okay, and this is with this the top surface. Here we'll put the area of the top surface. Again E dot ds, here we'll put suppose the bottom surface, this one. Again E dot ds for curved surface, okay, curved surface. So we'll get the total electric flux linked with this cylinder. Okay, now instead of writing all this separately, we can also write this in this way: E dot ds linked with a whole closed surface area. So this is the closed integral. If I expand this, I'll get this one. Okay, so electric flux is how much? Closed integral of E dot ds. Closed integral E dot ds means this one. If I expand this, we'll get what? The top surface, just a minute. The top surface, the bottom surface, and the curved surface area. The curved surface. Okay. So this is what the electric flux linked with the closed surface. Next, what is, now we are ready to study Gauss's theorem. Okay, next, Gauss's theorem. So it states that for any distribution of charges, the total electric flux linked with the closed surface is 1 by epsilon naught times the total charge contained within that closed surface. What does this mean? The total electric flux linked with the closed surface. So always remember that this Gauss's theorem is always applicable to the closed surface. Okay, so this Gauss's theorem is always applicable to the closed surface. So the closed surface electric flux linked with the closed surface is how much? 1 by epsilon naught times, we all know that epsilon naught is what? Epsilon naught is, we have studied in the previous part, epsilon naught is the permittivity. Okay, since I've written naught, say permittivity of free space, or we can say permittivity of air. Okay, and we all know the value of epsilon naught is 8.85 into 10 to the power minus 12. Okay, so this was what we have studied previously. So 1 by epsilon naught times the total charge contained within that closed surface. Suppose there is a closed surface. So this is the closed surface, and the total charge is Q. So the electric flux linked with the surface, the electric flux linked with the surface. Always remember, electric flux is always linked with the surface, and Gauss's theorem, electric flux is linked with the closed surface. So this is the closed surface. Okay, so this is the closed surface. Now they have said the electric flux linked with this closed surface is Q by epsilon naught. That is what they have said, 1 by epsilon naught times the total charge. So 1 by epsilon naught times, see, 1 by epsilon times the total charge, and total charge is how much? Is Q. So that is Q by epsilon naught. So this is the Gauss's theorem. We have also studied that electric flux for a closed surface, see, electric flux for a closed surface is how much? E dot ds. So we can also write this as, instead of phi e, we can write E dot ds close integral is equal to q by epsilon naught. Okay, so we can say that this is the Gauss's theorem in vector form. This is Gauss's theorem in vector form. So this is the Gauss's theorem. So Gauss's theorem is what? It states that for any distribution of charge, the total electric flux, this total electric flux linked with what? The closed surface is always 1 by epsilon naught times the total charge. The total charge here, it was q, so I have written q. So q, so we can write phi e for the closed surface is E dot, okay, E dot ds, and there is a closed integral is equal to q by epsilon naught. Okay, so this was Gauss's theorem. Next we are going to do proof for Gauss's theorem. Okay, see. So to prove Gauss's theorem, what we do, we take a charge q, okay, and we take a surface. Suppose this is a closed surface, and here we have to find on this surface we have to find the electric flux. Okay, and what is Gauss's theorem? We are proving Gauss's theorem means we have to prove, that is required to prove is phi e is equal to q by epsilon naught. To prove Gauss's theorem, it means we have to prove this. Okay, so now we know that for this q, suppose here this distance is r, it is a sphere of radius r. Now electric field will be in this direction, okay, because it is a positive charge and positive, so electric field will is always, electric field is a vector quantity, so here it is a charge q, and here we have to find. So what we do, we put here a unit positive charge and this unit positive charge. So here this is also positive, so electric field will always be outward. Okay, so this electric field means the force will always repel it, because here it is what, positive, and this is also positive, so there will be a repulsion, so force will act in this direction. Similarly electric field also act in this direction, so electric field will be in this direction. Okay, now next we have to find what? Surface. So we take a very small surface, and here the area vector will be perpendicular to the surface, so area vector will also be in the same direction. So we can say here the theta will be 0 degree. Why? Because E and ds both are in the same direction. Okay, so what are you doing? So q charge is placed, okay, q charge is placed at the center of spherical shell, okay, and a point P. So we take this point P is on the surface. Okay, so what will be the electric field? Electric field at point P will be 1 by 4 pi epsilon naught into q by r square. We know this, that electric field is 1 by 4 pi epsilon naught into q by r square. So at this point electric field will be 1 by 4 pi epsilon naught into this charge divided by square of the distance, that is r square. So this is the electric. So what will electric flux? So according to Gauss's theorem, d phi e will be equal to E dot ds. Okay, now to find the electric flux linked with the whole surface, we integrate. Okay, now we have already found out that E and ds, see, E dot ds, we can write this as E ds cos theta, and theta here it is 0 degree. So E ds, cos 0 degree is 1. So here this will be phi E, here it is E ds. We can take E outside because E is constant. So E, here we are going to integrate only ds. Okay, now phi E is equal to E and ds. So what ds, ds is what? Total surface area. So total surface area of what I have taken this, a spherical shell. Okay, so here total surface area of a sphere is 4 pi r square, and electric field is how much? We have taken 1 by 4 pi epsilon into q by r square. So 1 by 4 pi epsilon naught into q by r square, and here it is 4 pi r square. So this is 4 pi r square, this is phi e. Now see, this 4 pi and this 4 pi got cancelled, this r square got cancelled. So we are left with only q by epsilon naught. So phi e is equal to q by epsilon naught. So proved. Okay, so we have proved what? The Gauss's theorem. So we have proved Gauss's theorem. Okay, so till now what we have studied. Okay, let's summarize it. First we have studied about electric flux. What is electric flux? So just remember that electric flux is always linked with the surface area, okay, and electric flux is a scalar quantity, and electric flux is equal to E dot A, where A is what? Area vector, and area vector is what is perpendicular to the surface. Area vector is always perpendicular to the surface. Okay, next we have studied that if we have a cube within an electric field, the electric flux is 0. We have already shown. I have already showed you. Okay, next electric flux linked with the closed surface, and that too irregular one. So how we write? Phi is equal to E dot ds, and there will be a closed integral. Okay, next we have studied about Gauss's theorem. Gauss's theorem is what? The total electric flux linked with the closed surface. Always remember that the total electric flux linked with the closed surface is how much? 1 by epsilon naught times the total charge contained within that closed surface. Okay, that was phi is equal to q by epsilon naught. Then I have done the proof for Gauss's theorem. Okay, next day we will study about the application of Gauss's theorem, and we'll meet you in the next class. Okay.